Alright, so here is the video as promised, uh, acid-base practice. And so in the first one here, we're going to look at actually atomic size to make our determination. And what we can see is that, of course, the sulfur is larger than the oxygen. And since sulfur is, in fact, larger than oxygen, if it's below it on the periodic table, the sulfur can kind of handle a little bit more of that negative charge that is there. Let me come into the end of my little screen here. So sulfur can hold that negative charge much easier. And so therefore, if that is the case, then it's basically going to be more stable. And so the sulfur in this case, the SH there, of course, which is the H is our acidic proton, is going to be more acidic because the sulfur here is more stable as the conjugate base. So the difference between the two is basically atomic size. Sulfur can kind of handle that negative charge a little bit better. In this one, the one here below, we're looking at resonance being the main difference that we have here. So if I draw the conjugate base for the first one, we see that basically I have all sp3 around it. There are no resonance structures, nowhere to move this negative charge. So there are no structures here that I can move this around. The charge is isolated on the oxygen. If I look at the one to the left of it, you can see that if I draw the conjugate base, I do, in fact, have a pi system, and so I can draw resonance structures all the way around. I can kick these electrons into the pi system, which forces me to move one out, because I can't have a carbon with 5 bonds. And if I draw the resulting resonance structure, you can, in fact, see that the negative charge that was on the oxygen is now moved over to the carbon, because I've moved those pi electrons. Then we can continue to draw and basically draw these resonance structures and move the charge all the way around the ring. So let me draw the last one here. And then you can see that sort of I'm running on the end of the screen here, but the negative charge is now on the carbon to the left of the C double bond O. So in summary, for this one, I have more resonance structures. It means that I can move the charge around that's on the conjugate base, which then stabilizes the conjugate base, right? And so the more stable the conjugate base, i.e. the weaker the conjugate base, which means the stronger the acid. So this one is, of course, more acidic.
It's science.
All right, let's look at the rest of these here. And in the first one, I'm really looking at the inductive effect. So remember that this is due to the large amount of electronegativity that's on an atom that is pulling electron density away. So fluorine here is strongly electronegative or withdrawing. And so we have to think about what that's going to do in terms of the charge. And so what this is going to do is actually stabilize the charge that is on there by pulling electron density away from it But remember, it's inductive effect, so it's only through the sigma bond framework. We're not moving pi electrons, right? So we're going to actually pull electron density away from that charge. This is a stabilizing effect. This means that what we're going to do, in fact, is make the conjugate base more stable. So that, in turn, makes this more acidic. All right, so in these guys, we need to circle the ones that are going to actually be acting here as our acidic protons, and I have those circled for you. And what we're looking at in this case is, in fact, hybridization, so differences in hybridization. And in this case, I have sp2 hybridized CH, and I have sp hybridized CH. And the one that turns out that has more S character, that is the one that's going to be the more acidic, right? And the reason is because the higher amount of S character can handle or kind of stabilize that negative charge better. So here I have sp on the left, sp2 on the right, and this makes this one more acidic. And this, again, is just due to the higher amount of S character. So this means that my conjugate base here is more stable, which, as you've guessed by now, implies that you have something that's more acidic. All right, so in this case, we're going to look here. So we have these NH protons or the OH protons that we're looking at here. And the big difference between the two is electronegativity. Oxygen is way more electronegative than nitrogen. And so oxygen, turns out, can handle the negative charge a little bit better than nitrogen. So this R negative, or RO negative that we have here is a little bit better than the sort of equivalent of the RNH negative, right? So that means that this carboxylic acid, in fact, is more stable as a conjugate base, which is therefore more acidic. The last one deals with resonance. And basically, again, this is, can we draw resonance structures to sort of dissipate or delocalize the charge and keep it from being on one specific place? And so what are the acidic protons that we're talking about? Well, really, in the one here on the right, it's any of the CH bonds that we have. And the one on the left, we're looking at the end CH bond. So any of those three that are on either side. Remember that there's a CH3 on either carbon there on the end. So what's the difference here? Which one is more acidic? Well, we can just simply draw out these with a negative charge. So if I pull out a proton, that means I leave the electrons behind, and I've got a negative charge there that's sitting on my carbon. So just to show you, here's a base. We're going to deprotonate, which means we leave those electrons that are shared between the carbon and hydrogen. They stay on the carbon. So this could either happen basically on any of the carbons that I've shown. And basically what we're looking at is that there are no resonance structures to be drawn for this one. I can't move that negative charge anywhere. However, if I draw this one and I do the same thing, and again, I'm coming kind of to the end of this sort of screen piece that I have here that I'm writing on, so I'm going to kind of put it underneath it. What you see is that I now have a negative charge, but there's a pi system right adjacent to that. So that means that I can actually draw a resonance structure and I can move the charge over to the oxygen. So I have more resonance structures that I can draw, and that means that this is more acidic because the conjugate base is therefore more stable.
Awesome.
All right, let's look at the last bit here. And the first thing you need to do in this case is recognize that we have an ionic compound here. And I have NH2-, which is a strong base. And our acidic hydrogen is the one that's actually drawn for you. And this is our acid-base reaction that we're looking for. And so what we see is I, in fact, have a negative charge now on the carbon. And I'm going to have ammonia. And then we can throw in our little sodium spectator ion hanging around. So this is our sort of acid-base reaction that we're looking at here. And the question now is, in which direction does the equilibrium lie? Well, we can do this or figure this out by looking at the pKa's. And so if I know that nitrogen-containing compounds have pKa's that are in the upper 30s, and this carbon triple bond CH has a pKa of roughly 25. That's one that you're going to want to kind of put in the back of your head there. And so we can see in this case that the equilibrium, in fact, is going to shift to the right, always towards the weaker acid. What about this one? All right, so this is really no different. I threw this in just to give you another example of this, but basically it's the same as you would draw if you had water, except now I don't have an extra hydrogen. I have an ethyl group there. So we got ethanol and benzoic acid here, and that's the acid-base reaction that is going to take place. And here we have our conjugate base. And our conjugate acid. So now we just need to look and figure out our different pKa values to determine the direction of the equilibrium. So remember, carboxylic acids, we said that they have pKa's that are roughly 5-ish. And then protonated oxygens are typically going to be somewhere in a negative range of pKa. So it's very strong. So in this case, that means our equilibrium now is going to lie to the left. All right, so I hope that this helped you guys. Thanks for watching.